So the first force acting upon the object is going to be the applied force, and then there's also going to be friction, which is along the surface of the where the object is, and then there's also going to be F of n and F of g, which are going to be equivalent to each other because it is not moving in any y direction. And then when you consider the displacement in the x direction with no vi, it's going to be 1/2 at squared. And then when you isolate for acceleration, it's going to be 2 delta x over t squared, which is acceleration. And then, as we know, rise over run, so it's going to be 2 delta x on the vertical and then t squared on the horizontal. And then for the table, I put the values of 2 delta x and then t squared, and then I simply just doubled the x values that they gave us, doubled the x values that they gave us in the table already, and then I also squared the t values that they gave us as well. So for the graph, I basically graphed what I put in the table. So like I said, the vertical axis is going to be 2 delta x, and then the horizontal axis is also going to be t squared, and 2 delta x is going to be in the units of meters, and then t is going to be in the units of t squared is going to be in units of second squared. So thus it being equal to like acceleration because meters over second squared. Yes. And then basically what I did is I scaled it by the values I had in the table, which is like 0.04, and then from there 0.26, and then from there 0.55, and then lastly 0.81. Oh, not lastly, actually. And then lastly, for Rose's time, 1.64. And then for the y-axis, I also took the values I had from the table, so 0.072, 0.468, 0.986, 1.45, and then 3.042. And then from there, I just plotted the points on the graph. Furthermore, for D, for the experimental A, what I did for the acceleration is the change in 2 delta x and then over the change in t squared, because that's going to get you basically the slope of the graph that I just graphed, and as we know, meters over second squared is acceleration. So I just picked 2 points and then I found the slope between them, and then from that I found out that the acceleration of the, I guess you could say, of the system or of the block is going to be 1.8 meters per second square. And then for part E, I used Newton's second law to derive an expression for mu k, so we know net force is equal to ma, and then I put the two forces that are acting in the x direction, so f of x and minus f of k equals ma, and then when you expand that, it's f cosine minus fn mu k equals ma, and then f cosine minus ma is equal to fn mu k, which is after I add fn mu k to both sides and then subtract ma to both sides. And then after that, you basically just isolate for mu k. So what I did was I divided by mg plus f sine theta, and then that will get me what I need for the equation for mu k. Okay, and then next, in the situation that the applied force is 12 and the angle is 60 and mass is 2 kilograms, calculate the kinetic frictional force. So basically, I'm going to use what I used in the last part, so f cosine theta minus ma equals fk, which comes from Newton's second law. And then I simply just substitute in the values that need to be substituted. And then from there, you solve for f of k under those initial or given conditions, which is 2.4 newtons. So for g, what I'm going to do is I'm going to do f of k over f of n is equal to mu k, and we know that 2.4 is f of k, so I just need to divide by f of n to find the mu k. And then earlier I didn't mention, but earlier I wrote down that the f of n is mg plus f sine theta, and then you just divide by 2 times 9.8 plus f sine, or 12 sine 60. And then when you simplify that, you will get mu k, and mu k is going to be equal 0.08. And then when we find that the applied angle is decreased, it is going to have it's going to increase the acceleration, just because, yeah, when the applied angle is decreased, the acceleration, I don't know why I wrote increased. Anyways, yeah, scratch it off. When the applied angle is decreased, then the acceleration is going to increase because f of x is going to increase. And since f of x is increasing, therefore there's more, I guess you could say, net force. Therefore, there will be more acceleration. And then from there, basically, you're just graphing the graphs now. So after that, what I did is I found that a of t is a constant, and then when you do the integral of that, you're going to get v of t, which is 1.8t. And then for the last graph, I simply just graphed the different values that were in the table given to us. So for the AFT graph, the y-axis is going to be acceleration, and that's going to be in meters per second squared, and then the x-axis is going to be time, which is going to be in seconds. And then I simply just scaled it by the time that's given in the table that's given to us. Yes, and then after that, since a is a constant, I simply just graphed like a straight horizontal line across the graph. And then for the next graph, basically what I did was I graphed the velocity versus time graph, and I found the equation for that earlier. So for the y-axis, it's going to be velocity in meters per second squared, and then time in seconds. And then I did the same. I did my scaling for the x-axis based off of the graph or the table that was given to us. So yes, and then from there I simply just plugged in those times into the VFT function that I found earlier. So then I just plot those points, and that should be a linear graph but with like a slope. And then for the last graph, basically what I did was I did x of m and versus t. So the y-axis is going to be x in the units of m, and then the x-axis is going to be t in units of seconds, and then I scaled accordingly just like I did the other ones, and then I just took the values from the table that was given to us, and then I plotted those points as well.